So reminding you guys again, the title for this course is Trigonometry. We have yet to do any trigonometry yet in this course. That changes today as we start talking about trigonometry. So the introduction is kind of over. We reviewed talking about functions. We're now going to start developing these trigonometric functions that we'll spend the majority of this first semester studying. Hopefully from your geometry course a time ago, you remember that angles were a central part of studying trigonometry. So we want to go and talk a little bit more about angles, review some of these geometric concepts, and introduce to you a second way of measuring angles. And that's going to be the focus for kind of today. So our first definition is for this term central angle. So the central angle has a measure of 1 radian if it intercepts an arc with the same length as the radius. Actually, I guess radian is really the word that we're defining here. So let's kind of review what we mean here by some of these things. So when we say central angle, what are we talking about? We're saying that if I have a circle and we make an angle whose vertex is the center of that circle, so angle CAB is a central angle. Everybody okay with that idea? So if A is the center of the circle, that means that AC and AB are radii. Remember, a segment from the center of the circle to anywhere on the perimeter of the circle is a radius. Everybody okay with that vocabulary? And what we're saying here in our definition is that if the arc BC, and remember the symbol we use to represent an arc of a circle is we just use the 2 letters and then put the like a little arc hat on top of it. So if that measure of that arc is congruent to the measure of the radius, then we can say the measure of that angle CAB is equal to 1 radian. Now this probably sounds unfamiliar because what are we most used to measuring angles in? Degrees. Is a radian the same as a degree? No, what we're doing when we're describing an angle measure in radian is we're describing basically kind of the length of that arc of the circle that the angle would be embedded inside of. So what's natural is to want to create a way to translate back and forth between degrees and radians. Just like if you're learning a new way to measure something, if you want to measure something in feet and you're introduced to the idea of a meter, you want to have a way to convert back and forth between feet and meters. You want to have a way to convert back and forth between degrees and radians. Okay? So let's think about a way to do that. Yeah, all right, we'll make a new one. So let's say we have a circle with a radius of 1. Well, we know that if I take the angle CAB, that's 360 degrees. Everybody agree with that? And I know then that the length then from CA to CB, I'm sorry, of the length of arc CB is going to be 1/2 of 2 pi r. Remember that 2 pi r is the formula for the circumference of a circle. And that green part, the arc CB, is exactly half of the circumference of our circle. So I can just write 1/2 of 2 pi r. And we know the radius in this case is length 1. So what we're left with is that measure of arc CB is 1. So what I can say is 180 degrees is equal to pi radians. Yes. Yeah. Correct.
Okay.
Yep. 1/2 times 2 is 1, and then 1 times pi is pi, and then pi times 1 is just pi again. Yes, exactly right. So let's do an example here of using this. So just like you did in your chemistry class or other science class, I'm going to do a unit conversion. So I'm going to have 90 degrees, and I'm going to multiply this then by a conversion factor. My conversion factor is that 180 degrees is pi radians. So where should the 180 degrees go in this conversion factor? Should it go in the numerator or the denominator? It should go in the denominator. Remember that the units are always on diagonals of each other when we write our conversion factor. Do you guys remember that from your science class? So to convert 90 degrees to radians, I'm going to multiply 90 degrees by pi over 180 degrees. When I do that, I get basically 90 pi over 100 and 80. When I have 90 over 180, that can reduce, can't it? What does 90 over 180 reduce to? 1/2. So I will write that that is equal to pi over 2 radians. We okay with that one? Let's do another. Let's say we want to convert 152 degrees to radians. Well, we'll start with 152 degrees, and then we need to multiply that by some conversion factor. What should be in the denominator of the conversion factor? Degrees, 180 degrees to be specific. And what should be in the numerator? Pi radians. Yeah. Yes? So we looked for a way to relate a central angle that we knew in degrees, we know that this is 180 degrees, to the arc length of AB. We found that relationship is 180 degrees is central angle is the same as pi arc length. And since arc length is basically the same thing as a radian, we can say that 180 degrees is equal to pi radians. You're welcome. And so I can multiply 152 over 180, or 152 pi over 180 when I multiply that. Everybody's okay there? Notice I can reduce, but is the reducing going to be nice here? Not really. We could convert this into a decimal. It's not incorrect to do that. When the reducing is easy and obvious, we should probably leave it as a fraction, but there's nothing wrong with turning this into a decimal. It wouldn't be incorrect unless your directions told you specifically to give your answer in the exact form. So let's just type this into our calculator to illustrate that another way we could write this that isn't in terms of pi. So I'm going to do alpha and y equals to retrieve that fraction command. And I'm just going to type it in exactly as it looks on our sheet of paper. Oops. To get the pi button, you press second and then this exponent up, or the exponent button there underneath the clear. So I can say that 152 degrees is approximately 6.53, say, radians. Oh, 2.653 radians. Yes. Thank you. Again, if it feels like I just did something wrong, please speak up and say something. Everybody makes mistakes. I just made one there. Everybody feel okay about going from degrees to radians? Let's do a couple of examples where we go the opposite direction. So let's convert 2 pi over 5 radians into degrees. So I'm going to start with the measurement I know. And then I need to multiply this by a conversion factor. What should be the denominator of this conversion factor? Pi radians, again, because my units have to line up diagonal. Since I have units to start with, or radians to start with, the denominator needs to have radians in it. And the numerator should then be 180 degrees. Everybody happy with that? So when I multiply these fractions, we multiply straight across. 2 pi times 180 is 360 pi. And 5 times pi is 5 pi. Everybody okay to there? And now we can do some reducing, right? I notice that I have a pi on the numerator and a pi in the denominator. So those can cancel out. And then 360 divided by 5 is a whole number. That reduces to 72 degrees. Again, if you don't believe me, you can check that on your calculator, that 360 divided by 5 is 72. I promise you it is. Everybody okay with that? Okay. So remember, a radian is just like an arc length. So those radians could be written in terms of pi, or they could just be written as a decimal. So maybe I want to convert 1.6 radians to degrees. So again, I'll start with the measurement that I'm given. And I'm going to multiply that by what conversion factor? 180 degrees over pi radians. So when I do that, I'm going to get some decimal. Let's use our calculator to get that. Notice that there's not a pi in my 1.6 radians to cancel out, so there won't be an easy reducing to do. I'm just going to do 1.6 times alpha y equals, pick my fraction command, and I'll type in exactly 180 over pi. And then we'll hit enter. So that this is about 91.673 degrees. Yes, Hannah. Yes, that's doing the same thing. Mhm. Is everyone okay with that idea? You feel pretty good about converting back and forth from degrees to radians or radians to degrees? Okay. Remember again what the definition for a radian is if I have, say, like some 72-degree angle, if that angle is the central angle in the inside of a circle, the arc length of the circle that runs between the two arms is going to be that radian measure. In this case, this was 2 pi over 5, right? So again, degrees are basically measuring this kind of an angle. A radian is giving an equivalent measurement. It's giving the length of that arc. Okay with that? So you can use either one of them. You can use them interchangeably. Okay with that? Let's continue on. We're going to do another definition here. So if we have some central angle that we'll call theta, again, this symbol here is the Greek letter theta. In trigonometry, we often use that symbol to denote an angle. So an unknown measurement in an angle, we'll often use the variable theta to represent that. In a circle with radius r, then the length of the intercepted arc S is given by the formula S is equal to r times theta. If theta is measured in degrees, this formula becomes this. Why is that happening? What's the difference between these two formulas? Just this pi over 180 piece. Everybody agree with that? So for this formula to work, our angle has to be measured in radians. If our formula is or if our angle is measured in degrees, I have to convert that degree measurement into radians, right? What is going to happen if I multiply theta by pi over 180? It's just converting that angle measure back into radians. So we're back at the previous. Okay with that? So notice that the formula for degrees is really no different than the formula for radians. We just have to tack on this extra conversion factor at the end that transforms our angle measure back into radians, so we can apply the previous formula. Let's look at an example. So let's say we want to solve for S if R is 1.4 meters and theta is 0.98 radians. Which of the two formulas do I want to use, the first one or the second one? They're both solving for S. Good. I should use the first one. Why? Well, you're given the angle in radians, right? I think that's what you meant. So we're going to use the formula S is equal to R times theta. And if you type those into your calculator, you get 1.372 meters. That's embarrassing. How about this one? We're told to solve for S if R equals 3.8 inches and theta is 40 degrees. Which formula for S should we use? Yeah, we should use the one that is in the degree form that has that extra conversion factor already built in. Or you could think about converting the degrees into radians and then using the previous formula. Either way of approaching the problem is fine. I'm going to think about it as if I'm using the second formula. And when I type this in, I get about 2.653 inches. So here we're asked to solve for r. To solve for r, if s is 18 centimeters and theta is 2.13 radians. So which formula would I want to use here? The first one or the second one? The first one, because the angle measure we're given is in radians. So to solve this, I'm going to plug in 18 for S and 2.13 for R. And if I divide both sides by 2.13 and then type that into my calculator, I get 8.451 is about my radius for that circle. Because I rounded that. If I type that in my calculator, there's a lot more decimals there. So when I use the squiggly lines like this, instead of a straight equal sign, it means that I did some rounding. There's an approximation present there. Notice up until that point I had straight equal signs because those two things are equal. No rounding had occurred. But as soon as I do some rounding, I'm going to change those to squiggles. Okay with that? And if you're working with radians or doing much of your trigonometry, it's going to be kind of a rare occurrence or a special occurrence to get exact answers that don't require any rounding. So we'll do a lot of rounding in this course. But we'll also spend a fair bit of time talking about those situations where we can find exact solutions as well. All right, let's do some more. So D says, find the perimeter of the sector with a central angle of 1.7 radians, cut from a circle with a radius of 5 centimeters. Let's start by reminding ourselves what we mean by a sector. This was a piece of geometry vocabulary that we might not remember. A sector is basically just a slice of pizza. And when I talk about a slice of pizza, I mean from a round pizza, not a Jets pizza. So our sector is going to look kind of like this. Everybody okay with that? So this is cut out of some larger circle. Boy, that's terrible looking. Let me use the circle tool to kind of clean up my art skills here. Art's hard, guys. Yeah. Are any of you guys good artists? Yeah. Terrible. I've never in my academic career taken a fine art class. So that's a little better once I use the circle tool on the OneNote. So let's label the parts of this then. So we know that the radius for this circle is 5. And I'm going to give these points some names so it's easy to talk about. Everybody is okay with that? And we're told that the central angle here is 1.7 radians. Rad, R-E-D, just short for radian. Everybody's okay with that? The question is asking for the perimeter of that sector. So that perimeter is going to be this side plus this side plus this side. Everybody agree with that? If the perimeter is just the distance around, so it's going to be AB plus AC plus the arc BC. So far, so good? Now, AB and BC are really easy to get, right? We labeled those already. Those are each 5 because they're radii of the circle. How am I going to calculate BC? I know that BC is basically my arc length, and I can calculate an arc length for a circle by doing r times theta, where theta is measured in radians, which is the situation we have here. So here we have 5 plus 5 plus 8.5. So that's 18.5, and I think we said the unit here was in centimeters. So we have 18.5 centimeters. Is everybody okay with that idea? Let's do another example. What letter are we on? E, I think? Is that right? So this problem says a car has 18-inch diameter tires on it. If the car is traveling 15 miles per hour, how many revolutions per second are the tires making? So when I read revolutions per second, this word, or this quantity they're asking for, is a rate. What word in there tells me it's a rate? per. Are we given another rate in this problem? Yes, what is it? Miles per hour. So my goal is to convert miles per hour into revolutions per second. Everybody good with that plan? Okay. So I'm going to start by writing 15 miles, and then per really means divides, 1 hour. And we're going to do a bunch of stuff and spit out the other side. We're going to have some number of revolutions over some number of seconds. Everybody okay with that plan? Okay. So the first thing that I'm going to worry about is converting hours to seconds, because we know how to do that, right? What would I want to do first to convert hours to seconds? Let's convert hours into minutes, right? How many minutes are in an hour? 60. So in my first conversion factor, where should the 60 minutes go? On top or bottom? Bottom. And on top should be 1 hour. So when we do that, the hours will cancel out. Good. And we're left with the denominator in terms of minutes, right? What unit are we trying to get to, though? Seconds. So let's do it again. How many seconds are in a minute? 60. So what should go on top? 1 minute. And again, boom, ba-doom. So now we've done the denominator part. We've converted hours to seconds. What we still need to do is convert miles into revolutions. That's a little bit trickier. What other piece of information have we been given here that we haven't used? 18-inch diameter tires. So let me ask the question, how far is 1 revolution? If you rotate your wheel 1 time, how far did that wheel go? 18 inches. Everybody okay with that? So I know 1 revolution equals 18 inches. That's the second conversion factor I want to use. However, my distance measurement is in miles and not inches. So before I can use that conversion factor, I need to convert miles into inches. Now, I don't know how many inches are in a mile straight away, but I do know how many feet are in a mile. 5,280? Okay. So there, miles have canceled and we're left in feet. But what unit do we want to be in? Inches. So we need one more conversion here before we can use that revolutions conversion. How many inches are in a foot? 12. And now I can use that I get 18 inches to 1 revolution. Everybody okay with that? All right, let's punch this into our calculator and get an answer here. Yeah. I would give you that kind of a conversion, I suppose. Or I would give you something that's instead of miles per hour, it would be like feet per hour. So I avoid having to use that particular conversion that's unfamiliar. I would hope that you have the feet, number of inches in a foot memorized. Or I might use SI units where I might give you like kilometers and centimeters or something, where I know you know all the conversions for those. They're all base 10. Okay, so the way I'm going to do this, I'm going to press alpha y equals, select the fraction command, and I'm going to write the multiplication problem for the entire numerator. So I have 15 times 1 times 1 times 5,280 times 12 times 1. Everybody okay with how I wrote the numerator there? Again, I just read straight across here and did 15 times 1 times 1 times 5,280 times 12 times 1. Everybody good with that? We'll do the same thing here for the denominator. So I'm going to do 1 times 60 times 60 times 1 times 1 times 18. And I'll press enter. Okay, so it's going to just be a duty head. So if I type in 44 over 3, I get about 14 point, oh my gosh! I'm so stupid. Stop. Stop, 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 stop. That's way too much. What's my mistake? That number is not 18. No. So let's think about it. So here's my wheel. Here's the ground, right? If this point, we just unravel this wheel, like if I cut it right here and lay it down, how far is this? That's not 18 inches. Definitely we can see that, right? How far is that? It's the circumference for the circle, right? It's the distance around the edge, which in our case is 2 pi r, which is 36 pi. Ay, ay, ay. Okay. No, but I would be happy to re-explain what happened here right now. Hannah, what are you confused by? Oh my goodness. But that's the diameter, not the radius. That's what you're confused by. So it should be 2 times 9. Thank you. I'm glad you said something. Thank you, Hannah. I'm glad you spoke up. You ask questions? Things that were confusing got less confusing for some of you and more confusing for others of you. which is okay. Kendall? No? No, you don't get to get away with that. You just said you're so confused. Okay. When was the last part that was processing in your brain? Let's go back. Let's backtrack to that. Okay. So let's recap again what we tried to do here. So we were told a car has 18-inch diameter tires, and it's traveling at 15 miles per hour, and we want to find out how fast in revolutions per second those tires are spinning. Okay? So our answer that we're looking for is a rate. It's revolutions per minute. So it stands to reason that the rate that we were given in the beginning, miles per hour, I need to convert to revolutions per minute. Okay, with that as the general plan. So I'm going to convert one rate to the other rate. Now, to convert from miles per hour into revolutions per second, the first thing we did was converted hours into seconds. So that was the first two conversion factors. I converted first hours to minutes, and then minutes to seconds. You feel good about that? Okay. The next thing I did is I wanted to ask was how far does the car go with one tire revolution? So I'm imagining I have my tire here on the ground. If I cut my tire and I take this end and lie it up over here, this length that the tire makes is one circumference of the circle, right? Because that's the distance around the outside that I've just kind of chopped off and laid flat. Does that make sense why that one revolution is one circumference? So then I use my circumference formula from geometry. The circumference is equal to 2 pi r. And in our case, if our diameter was 18, our radius is 9. So I have that my circumference is 2 times pi times 9, or 18 pi. So I plugged in 8 pi here, and now I'll go back to my calculator and fix this. And not 18 pi, because I forgot to do the circumference. So if I do that now, that's much more reasonable. So 4.67 or 669 revolutions per second. Kendall, does that feel better? You know what? If you're confused and you need to hear it again, just say something. And you're not the only one that I'm sure is confused and is glad to hear it again. Okay? Right? Who else feels better about this walking through it one more time there at the end after everything is sorted back out? See? Lots of people raised their hand. You weren't the only one that was like, yeah, I need to hear that one more time. Okay? Good. Jeepers. Let's just stop here. There's 5 minutes left or whatever.